good evening, or good morning, or good day. Today we are going to talk about reducing radicals. But before I do, I usually save this part for the end of the video, but I would appreciate it if you would like this video and subscribe to my channel. Usually at the end, people are asleep, so you don't hear that message. So do that now. I would greatly appreciate it. And then you can fall asleep while you learn some math. Learn or review, depending on where you're at. All right, so let's start with very simple ideas of reducing numerical radicals. And radicals are, of course, square roots, although you can have the third root or the fourth root or any number of roots. But we're just going to stick to the second root or the square root for what we're talking about today. And we're going to start with a really simple idea of just reducing to simplest terms, something like radical 20. Now, of course, when you have the square root of a perfect square, like the square root of 4, you just get what that square root is. The square root of 4 is 2, and that will come in handy here. The first step when dealing with just a number is to write two radicals. And the two radicals that you have, one should be a perfect square. I just said 4, so let's use 4. And then if I divide 20 by 4, I'm left with 5, and that's what goes underneath the other radical. As mentioned before, the square root of 4 is 2, and the square root of 5 doesn't reduce any further, and I just wind up with 2 radical 5. Pretty simple. Now, let's say I have something maybe a little bit more complicated. Like, how about the square root of 162? So there's actually a lot of numbers that go into 162, some of them perfect squares. For example, 9, and I will get back to that in a moment. But what might be helpful is if on the side of your paper, or whatever you're using if you're doing math along with me, write all of the perfect squares up to 12 squared. You don't necessarily have to include 1. I'm not going to. We have 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, and 144. You can go further if you like, but this is 2 squared, 3 squared, 4 squared, and so on all the way up to 12 squared. So what I like to do is I like to start at about the halfway point. If I know exactly what the halfway point is, great. If not, I want to pick something a little above the halfway point and find where that is in this list. Now, I happen to know half of 162 is 81. I picked that number for a reason. Let's pretend I didn't. I'd say, you know what, 100, that's greater than a half. Does 100 go into 162? It doesn't. What about 81? And I just told you that it does. Therefore, the square root of 162 can be written as the square root of 81 and the square root of 2. The square root of 81 is 9, and radical 2 doesn't reduce, so you wind up with 9 radical 2. What I like about this method is you are guaranteed, as long as you do your numerical computations correctly, you're guaranteed to not have to do extra steps. And what I mean by that is, let's take that same exact question, 162. And earlier I said that 9 goes into 162. So if instead of starting from the higher numbers and working my way towards the lower numbers, if I started at the lower numbers and started working towards the higher, it does still work, it just could take more steps. Does 4 go into 162? It does not. Does 9 go into 162? It does. How many times? 18 times. So I can write this as the square root of 9 times the square root of 18. And that's not wrong. The square root of 9 is 3, and I get 3 square root, or 3 radical 18. The thing is, radical 18 can be reduced further. I can now write this as 3 times radical 9 times radical 2, or 3 times 3 radical 2, which is 9 radical 2. The idea is, looking back at our example on the left, to find the largest perfect square that goes into a radical and an irreducible radical. Okay, let's look at something else. because of course things have to get more complicated. That's how algebra works. What if we didn't just have numbers? What if we also had some of those pesky variables in there? For example, let's say I had something like the square root of 150 x cubed. I always recommend that people write this in stages. Start with the numbers and then move on to all of your letters. So we just talked about the numbers. That should be pretty easy. 25 is a number from our list that goes into 150. And 25 times 6 gives us 150, so I get radical 25 times radical 6. When you're talking about variables, what you want to look at is your exponents. Because I break these up as well. Big asterisk. That's a terrible looking asterisk. Where's my undo? Much better looking asterisk. The asterisk is if you have an even exponent, you don't need to write two radicals for that exponent. I'll show that in the next example. When you have an odd exponent, what you do is you go one less than the exponent you see, so x squared, and then put just that variable on its own, because x squared times x is x cubed, therefore x cubed can be rewritten as x squared times x, and of course all of these things are underneath the radical. Once I have this set up, now I can go through one radical at a time and either reduce or note that it is irreducible. So the square root of 25 is 5. The square root of 6 is irreducible. Put little tiny times dots in there. The square root of x squared is x, and the square root of x is irreducible. Now that we have simplified all of our radicals individually as far as they will go, the last step is to just recombine everything. Anything that is not underneath the radical goes together, and everything that's underneath the radical goes together under one radical. So in this case, we get 5x radical 6x. So now let's look at an even more complicated example. Let's see the whole thing in action. So let's go with the square root of, how about 108 x squared y to the 5th z to the 7th. That's a nice big ugly radical. So first I need to make square roots for my numbers. So I don't know what the numbers are going to be just yet, but two numbers are going to multiply to 108. And I'm also going to have x squared y to the 5th, I'm going to want to rewrite as y to the 4th times y. Of course, each one underneath its radical. And with the z to the 7th, I'm going to write that as the square root of z to the 6th times the square root of z. So I've dealt with my letters, my variables. X squared, that's an even exponent. It only requires a radical over that expression as you see it. Times y to the 5th, that had to be broken down into y to the 4th and just y. Z to the 7th had to be broken down into z to the 6th and just z. Now we have to look back at these numbers, 108. If you are just looking and saying 108, oh, I know my 9's trick, 9 goes into that. Once again, you're going to be correct. However, you will also find that you might be better off with something different. Let's go back to our square roots list. If I start at, say, what did I say that my number was 108, right? So about half of that is, 50 something. Let's start at 64. Does 64 go in? No, it does not. What about 49? No. 36. Interesting. 36 plus 36 is 72, plus another 36 is 108. 36 goes into 108 3 times, so I can make this radical 36 times radical 3. If you decided to go with 9 and 12, you would still wind up with the right answer. It would just take you a little bit longer. Now, we go through every single one of these radicals and either reduce or note that they are irreducible. The square root of 36 is 6. The square root of 3 is irreducible. The square root of x squared is x. The square root of y to the 4th is y squared. The square root of y is irreducible. The square root of z to the 6th is z to the 3rd. And the square root of z is irreducible. Everything that is not underneath the radical goes together. 6xy squared z cubed. And everything that is under a radical goes together under one big radical. 3y z. I hope you enjoyed. I hope you're asleep. If you're not and you didn't subscribe earlier, here's your chance to do it again. Feel free to check out my other videos, and we'll catch you next time.